Hello everyone. So we'll start the session in like 10-15 minutes, just waiting for a few people to join the session in person. So till then, everyone who's watching on YouTube, will I'll mute myself for like 10 minutes. If no one joins, then we'll start the session anyways. So I'll just mute myself till then. Okay, so I guess since no one has joined the session in person yet, we can get started nonetheless. So, just to reintroduce myself, hello everyone. I'm Lakshay Saggi, the problem solving TA for the Tuesday 6 to 8 p.m. sessions for the NPTEL sorry, uh, special topics in algorithms course. And I believe this is going to be our sixth session, and in this session, we'll be continuing our discussions which we had in previous week related to Markov chains and their application. So once again, since these are just problem solving sessions, we'll be before starting with the problems, we'll again be discussing a summary of whatever was discussed in this week's lectures. But of course, like I'll be assuming that you guys have seen the lecture videos before watching these sessions because like these 2 hour sessions are of course not a substitute for the extensive lecture material. So yeah. So keeping that in mind, maybe now we can get started. So I'll just share my screen. Let me just share my screen, guys. Yeah. So I hope my screen is visible to everyone. So yeah, maybe we can get started then. Uh, Continuing with the discussions of last week about Markov chains, we know what Markov chains are. We discussed a lot of properties about Markov chains in the last week. And just as a reminder of some of the properties which will be useful in this week, so which will be useful in this week's which were useful in this week's lecture videos as well as will be useful for the problem which we'll be solving later on, are that so, uh, so HII. So we introduced this notion of like hitting time in a Markov chain. So Hij it denotes the hitting time from the state I to state J, which is essentially, and what was hitting time? Hitting time is essentially if you start at a state I, if your Markov chain starts at a state I, then what's the expected number of steps after which it reaches the stage? It reaches the uh, state J. Like it can reach there in 1 step with some probability, it can reach in 2 steps with some other probability, and so on. So you have to take the expectation over all of these numbers, and yeah, the final number, the final expectation is the value Hij. And this is a really cool property that the hitting uh, the hitting time from state I to state I. So essentially, if you're starting at state I, then what's the next time at which you will come back to the state I? The expected time after which one comes back to the state I is equals to 1 over pi I, where pi is nothing but the yeah pi is nothing but the uh, stationary distribution value, or let's say if the Markov chain is like it follows the conditions which we had discussed in the previous session, like it's the limiting distribution kind of. Yeah. So HII is equals to 1 over pi I. We know how to calculate these pi i's. Uh, we discussed these last time also. And yeah, also the limit at like at t tends to infinity, nit divided over t is equals to pi I. And what is nit? So nit is n of I comma t, essentially is mm, so it's essentially till time t, how many times has the Markov chain hit the state I? Uh, so if you have started if you have started from a Markov chain, then suppose till time t, we have run through the Markov chain. Uh, we have run through the Markov chain following some probabilities. Then what's the expected number of times the state I has been hit? And this kind of a number is actually equal to pi I. And this is like not too hard to see also, like because pi I is essentially what happens in stationary distribution. Like stationary distribution can be thought of as like if the Markov chain is well behaved, then it's like a limiting distribution. So if at a very large point of time, like what's the distribution going to look like? It's given to us by these pi values, and essentially what these pi values denote are like the fraction of times each state is visited. in a limiting distribution. And this fraction can also be thought of in this manner: n of I comma t divided by t. N is just the expected number of times state I has been hit till the time t. So, and there was another important notion, which was commute time between states. So commute time between states I and j is just written as Cij, and it's just equal to like uh, we're trying to essentially like commuting from state I to j and then coming back. So essentially, yeah, hitting the state j from state I, so hij plus uh, going from like j back to I, so plus hj. So hitting time from I to j plus hitting time from j to I is equal to the commute time Cij or any pair of states. And then there was this really nice corollary. This was also discussed last week also. Like, so if we consider random walk on an undirected connected non-bipartite graph, then HII. Uh, so we know that uh, yeah. So then HII, the hitting time from like I to I is 1 over pi, which we already discussed, 1 over pi I. And in previous week, we saw that in a random walk on an undirected connected graph, this pi I takes the value di, which is like degree of the node I, divided by twice the number of edges. So then HII, the hitting time from like going from a state I to like coming to state, like starting from state I and then coming back to state I, the expected number of times that's taken is just equal to 1 over pi I, and this pi I is nothing but we know that degree of the node I divided by twice the number of edges. So this gives us that HII is equals to 2 times number of edges divided by degree of the node I. And this is like a useful property which one can keep in mind. And what this gives us is uh, and this gives a really cool lemma, which was also shown in the like lecture videos. I will not be going. So we'll be discussing all the lemmas and theorems on a very high level. We won't be going into the proofs of them because the proofs have anyways been discussed in the lecture videos. Uh, but yeah, this is also not too hard. But so if we consider a random walk on an undirected connected non-bipartite graph, then if I comma j is an edge in the graph, then the hitting time from I to j is actually less than equal to twice the number of edges in the graph. So this is not epsilon, this is e like. So hitting time from I to j is less than twice the number of edges in the graph. And turns out this property turns out to be really useful. So whenever we are doing like random walk on a graph, if there is an edge from I to j, then we can always say that hitting time from I to j is actually less than twice the number of edges. And what this gives us is this lemma actually results in this theorem. This proof of discussed also in the lectures that the so if we consider random walk on an undirected connected non-bipartite graph, then the cover time of the random walk is at most 4 times number of edges times the number of vertices. And what do we mean by cover time? So cover time is essentially if you start from any node in the random walk, then by what time will you be able to uh, like what's the expected time by which one will be able to reach all the nodes in the graph. Yeah. So if you're starting at one node of the graph in a random walk, then what's the expected time by which you'll reach you will have visited all the nodes at least once. Yeah. And the expected again this is a random walk, so this cover time for a certain walk will be like this will be a random variable, as its expectation is actually like 4 times number of edges times number of vertices. And this proof was also like not too difficult once this lemma is known. In this proof, just as a high level reminder, we we assume like since this is a connected graph, it will have a spanning tree, and if it has a spanning tree, then one can have a like a walk of length twice the number of vertices, approximately twice the number of vertices, which covers all the nodes in the graph. Essentially, that's a Euler tour of the spanning tree of the graph. And since between any pair of edges, the hitting time is at most twice the number of edges, and the arcbox length is at most twice the number of vertices. So the total cover time is at most twice the number of edges times twice the number of vertices, which is just 4 times number of edges times number of vertices. So yeah, I'm just revising the proof on a very high level, but yeah, you can look into it if you want to go into detail. So yeah. So after going over this, then there were discussions around like further like algorithmic uses of Markov chains. So some like one of the most useful or like widely used use cases are these Monte Carlo methods, essentially, which are used a lot in real world to like simulate a lot of experiments to find out values of certain constants and so on. So these Monte Carlo methods are used a lot actually in the uh, real world scenarios, and hence like we should know about them. But yeah, before starting with these Monte Carlo methods, essentially like let's just start with some definitions. So what's an epsilon delta approximation? So a randomized algorithm is said to provide an epsilon delta approximation of some value v of x. So suppose we are given some input x and we have to find out the value of some function, let's say v of x. For example, suppose you are given a graph as input and this v of x, like x is the input graph and then v of x is, let's say, the size of the minimum spanning tree, for example. Yeah, the weight of the minimum spanning tree or something like that. Yeah. So if we have to find some value v of x of the input instance x, or let's say we have to estimate this thing, and suppose our algorithm, whatever is our algorithm gives the output a of x. Yeah. Then then our algorithm A is an epsilon delta approximation, or this value A is an epsilon delta approximation if for all input instance x, the probability that A of x and V of x vary by at most epsilon is greater than equal to 1 minus delta. So essentially, let's just try to parse this statement for a second. Let's just pause and parse this statement for a second. What does this even mean? So essentially what this means is that what we are given is we are given an input instance x, and for this specific given input instance x we need to find out or estimate the value of v of x. But it might be that we are not it might be that computing this v of x is hard, or like we are not able to compute this exactly. So one might think, okay, we might approximate this. But in terms of randomized algorithms, okay, like maybe approximating also it might be that if you're using some kind of a randomized algorithm, then it might be that in expectation you are approximating or something, but it might be that sometimes the value is like sometimes the output a of x is very large, sometimes a of x is very small, and so it's kind of not reliable. In expectation it's good, but maybe like if we don't take expectation, but actually it might be a bad approximation. So but then what you can say is, okay, maybe like if we are able to guarantee that whatever output is, it is close to the actual output v with high probability. Like so if suppose if you are taking 1,000 instances, then out of 1,000 times, 999 times maybe our algorithm will be very close. Our output will be very close to the actual output. Then it's still like fine for us, and that's what we call an epsilon delta approximation. So what we are outputting the value a of x, and the target value is v of x. Then they are close if their difference is less than equal to epsilon. So uh, and like what we want is our algorithm should be as close to the actual value as possible, right? And so this should be so this thing should hold with very high probability, and this is greater than equal to 1 minus delta. So then it's called like an epsilon delta approximation. So some ideal goals for us will be maybe like an ideal algorithm, which will like an exact deterministic algorithm will be an algorithm which has epsilon delta both has 0. Because in that case, you will say that probability of a of x minus v of x is less than equal to 0, which means like a of x is equal to v of x, and that holds with probability at least 1, or exactly 1, you can say. So if for all input x, a of x and v of x have the same value, and with this holds with probability 1, then you can say then actually our algorithm is not an approximation, but yeah, it's an actual algorithm. So ideal goals in these epsilon delta approximations are usually to have epsilon delta as small as possible, right? And yeah. this epsilon delta approximation algorithm is called a fully polynomial randomized approximation scheme, or in short, FPRAS. Uh, uh, if the algorithm runs in time polynomial in the size of x, 1 over epsilon, and log of 1 over delta. So maybe let's just parse over this again, like why is it linear in x but inversely proportional to epsilon in delta? So this is because like as the input instance size grows, it's natural to assume, okay, that maybe the runtime of the algorithm will also increase. But if it increase polynomially with respect to input size, then it's fine for us in this FPRAS approximation scheme. However, uh, for these epsilon and deltas, we have an inverse relation because uh, like if as we said that we want these epsilon deltas to be as small as possible for to have a good approximation. But it's natural to assume, okay, if we are trying to provide more tight approximation, then maybe the compute time will go up. Like giving a bad solution maybe takes lesser time than giving a good solution. Like, and it's pretty natural to assume. And that's why, a good solution corresponds to uh, small values of epsilon and deltas. So if the values of silent deltas are small, then then it's kind of natural to assume that if the values of silent delta are small, then the algorithm runtime should increase. But if it increases polynomially, then like we are in this FPRS domain, and that's why like these are proportional to 1 over epsilon and like log of 1 over delta. So yeah. So why it's just one, like, so inversely proportional is clear, but then why again, like it's just 1 over silent, but 1 over delta has a log with it. So it's just it will so you can see the lecture videos and you can see like in the calculations and everything when you are doing like high probability, like we are doing guarantees with high probability and all, then the terms will be like the probability terms will be like e raised to the power log 1 over delta and so on, and that's why you kind of need to assume these as log of 1 over delta. But yeah, like you can see like the examples discussed in the lecture videos, and it will be a bit more clear, like why is this just 1 over epsilon, why is this like log of 1 over delta. But yeah, so this is what is FPRA, like fully polynomial randomized approximation schemes. Okay then, so uh, one example for this, Monte Carlo methods, this is one of the most famous examples, uh, is estimating the value of pi. Suppose, let's say we want to have an algorithmic way of computing the value of pi. So as we know, pi is an irrational, so we cannot compute the value of pi exactly, but can we estimate the value of pi through some algorithm? And I don't mean like just taking the value 22 over 7, but maybe some other methods. So yeah. So like I really like this kind of I really like this specific idea, although it's a like very widely known idea, but yeah, it's like really nice use of randomization and everything. So suppose so the our goal is to maybe estimate the value of pi, like what is the value of pi. So suppose we take a 2 cross 2 square in R. So in a plane, let's say we draw a square which has side length 2. So this is a square whose each side has a length of 2. And in that, let's say we inscribe a circle of radius 1. So in this square, let's say we inscribe a circle with radius 1 and diameter 2. So naturally, like this circle touches these four sides, right? And now let's say I take any point inside this circle randomly, like inside the square. So let's say in this square, what's the area of this square? The area of the square will be like 2 times 2, which will be 4, because like side length of the square is 2 and 2 square is 4. So this square has an area of 4. And what's the area of this circle? The area of this circle is the area of a circle is like pi r square, and r is 1. So area of circle is just pi, whereas area of the square is 4. And so now suppose I take a point uniformly at random in this square, like in this 2 cross 2 square, I take a point uniformly at random. Then uh, like since the area, then like what's the probability with which that point lies inside the circle as well? Like so I have taken a point randomly inside the square, so that point can lie inside the circle or it can lie outside the circle but inside the square in these kinds of values. So what's the probability with which that point will lie actually inside the circle? So it can be easily seen that like since we are taking the points uniformly at random, uh, the probability will correspond to like square area of the circle divided by like area of the square. So probability with which a point lies inside the circle will be just like area of the circle, which is pi, divided by area of the square, which is 4. So any point like a uniformly random point will lie inside the circle with probability pi over 4. So essentially like on a very high level, what this means is that okay, if I take a large collection of such points, like if I sample a very large collection of uniformly random points, then approximately pi by 4 fraction of those points will lie inside this circle. And then this, and also this fraction is kind of algorithmically easy to compute, like how many points are lying inside. So it's easy to take like L points. So suppose I take L points uniformly randomly from inside the square, then like then with the very high probability, like pi by 4 times L fraction of points will lie inside the circle. And from this what we get is yeah, so suppose the total number of points which actually lie inside the circle is k, which we compute is actually k, then pi by 4 times L is equal to k, and from that we can assume that the value of pi is just like, and from that we get that the value of pi is almost equal to 4k times L. So if this makes sense, like k was the number of points which we found from our sample L samples that lie inside the square as well, and then this 4k by L is just the our estimate of pi which we have computed now. So yeah, like yeah. And like this is intuitively, like this seems like a very nice algorithm. And then in the lectures we showed that yeah, like this indeed is a very good approximation with high probability also. So in the lectures it was shown that yeah, that I'll not go over the proof, but yeah, using Chernoff bounds, which you have already discussed, it was shown that the probability that our estimate is away from pi by an value of epsilon times pi with a probability less than equal to delta. And what's the number of samples which we are taking here? The number of samples which we have to take is like 12 divided by pi epsilon square log of 2 over delta. So yeah. So the number of samples. So yeah, again, like it's easy to see that one will need to choose more samples. If we are choosing more samples, maybe we'll get better approximation, because these kinds of like yeah, so because if you take larger number of samples, then yeah, our observations will be like our observed probabilities will approximately be equal to the theoretical probabilities. So that's why like yeah, and the number of samples should be inversely proportional to epsilon delta, because uh, we need to take more number of samples for better accuracy, but uh, more accuracy essentially implies smaller values of epsilon and delta. So yeah. So if we are given some epsilon and delta and we want to ensure that uh, like we want to give an epsilon delta approximation to the value pi, then to give an epsilon delta approximation to the value pi, we need to take at least this much samples for this algorithm which we just discussed. So yeah. So like since this is polynomial in 1 over epsilon and 1 over delta, log of 1 over delta, then yeah, it's actually a FPRAS algorithm for estimating the value of pi, if this makes sense. Yeah. So this is one really like this is a very well-known example, but yeah, nonetheless pretty cool idea to how to estimate value for estimating value of pi. Yeah. And then coming back to Monte Carlo methods, uh, yeah. Then it was after this estimating the value of pi, Another thing which was discussed was uh, designing a fully polynomial randomized approximation scheme for DNF counting problem. And what's DNF? So this will come up later, like these DNFs and CNFs. What are DNFs, CNFs? These kinds of discussions will come up later also when we are talking about like NP hardness and everything. But for now, like yeah, we'll just still discuss what are these. But you'll have to, but please keep these definitions in mind because they'll come up in future also. So 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 this like we are designing an FPRAS for DNF counting problem. So first of all, like what is even this DNF? Like what are we count? Like we are counting DNF. We are doing some counting related to DNF, but what even is DNF? So DNF is essentially like the full form of DNF is disjunctive normal form, and what this means is that like it's a Boolean formula written in or of and of literals. So a Boolean formula is in like its disjunctive normal form if it's written as like or of ands. So you take some literals, you take their ands, and you take multiple such uh, like literals and take their ands, and like all of these are merged by ors. So for example, let's say a function of this form, the x1, x2 bar, x3 plus x2, x3 bar is a formula in DNF. And why is this? So in note that there are these ors, and like this plus essentially corresponds to an or, and this or actually separates two formulas and both of these are just ands of literals. Like this is an and of x1 not x2 and x3, and this is an and of x2 and not x3. So this is in DNF form because this is an or of and. So because we are taking ands and then we are taking a final or. So yeah. So if we know what is DNF, then what is this DNF counting problem for which we will be for which it was discussed in lectures on like how to design an FPRA. So yeah. So the DNF counting problem is essentially suppose one is given a Boolean formula f in its DNF form as input, and as an output, one has to output the number of satisfying assignments of f. What's a satisfying assignment? So satisfying assignment for a formula is essentially an assignment of these variables, for example, here x2, x1, x2, and x3, such that that formula evaluates to true. So how many assignments are there uh, for which the given Boolean formula f evaluates to true? And that's the number which we want to output. But one thing to note is that, so this will come up later, that evaluating this number exactly is actually NP hard, like, and this notion will be like, what is NP hard? Will, if you are familiar with it, it's good, but it will come up later in like future sessions as well. Uh, but actually, yeah. So, but on a high level, like, uh, we do not expect to have a polynomial time algorithm to exactly count the number of satisfying assignments of a DNF formula. Uh, and this is because if one is able to count the number of satisfying assignments of a DNF formula exactly in like a polynomial time, like one can always solve this in exponential time because you just try like all the assignments, and out of all the assignments you just check how many of assignments are true. But if there are n variables, then you'll have to check like 2 to the n assignments. So that's exponential in the input size. So there exists an exponential time algorithm for this DNA counting problem, but like a polynomial time algorithm is something which uh, which might be hard, like which a lot of people believe that like one should not expect that these kinds of solutions will exist. Yeah, and why is this the case? Because then if one is able to exactly compute the number of satisfying assignments in a DNF formula, then one will also have a polynomial time algorithm for CNF that. And like what CNF? So DNF was disjunctive normal form, which is just like ORs of ands of literals. But CNF is like opposite of that. So in CNF, it's like a and of ors of literals. And the CNF stat problem is essentially, so in DNF counting problem, we were counting the number of satisfiable assignments. In CNF stat problem, we are just asked whether there exists at least one satisfying assignment to this problem. And actually, one can show that a CNF formula f over n variables is satisfiable if and only if its negation f bar has less than 2 to the n satisfying assignments. And that's why if we is able to count the exact number of satisfying assignments in its DNF form, so note that if f is in like CNF form, so it's let's say like CN like a formula f is given in CNF form, so that means it's written in form of like and of ors. So if you take its negation, if you consider formula f bar, then by De Morgan's law it will be like ors of ands of literals, and that will become the DNF problem. So if the f bar has less than 2 to the n satisfying assignments, if we are able to count the number of satisfying assignments for this problem f bar, then actually one we'll also be able to tell whether there exists at least one satisfying assignment for the formula f. And why is this true? Because suppose there exists at least one satisfying assignment for this formula f, then f bar then in f bar so for this formula f if there exists one satisfying assignment, then for that assignment of variables f evaluates to true, so f bar will actually evaluate to false. And that means if f bar evaluates to false, then it won't have the maximum number of satisfying assignments are 2 to the n. If there is at least one assignment at which f bar evaluates to false, then the number of satisfying assignments for f bar will be less than 2 to the n. And one can show the other direction as well. So this is this is the essential property that a CNF formula f over m variable is satisfiable if and only if f bar is less than 2 to the n satisfying assignment. And since I say if f is CNF formula, then f bar is DNF formula. So that's why DNF counting is like we do not expect a polynomial time algorithm for DNF counting as well. Yeah. So this is kind of the core property because of which we do not expect a exact polynomial time solution for DNF counting, and that's why we move to trying to find out some approximations for the DNF counting problem, like if we are actual output, like how many formulas satisfy this, how many inputs satisfy this DNF clause, this DNF formula, whatever we are given, can we like find an approximation to this, like the actual number of inputs which are satisfying the DNF. So yeah, what's a naive approach? What one might try, like what we did in the evaluating the value of pi. So what one might do is to count the number of satisfying assignments for this DNF formula. One might just try some random assignments from this 2 to the n actual assignment. Just pick some assignment of variables uniformly at random and check what fraction of the variables which we have actually satisfy the formula. So this approach, although on a high level it might seem that it's a good way to go about things, but actually this approach will not give us very good results. This is because to show that these kinds of formulas hold with high probability, usually we need like to apply Scherner bounds or something, and in those kinds of bounds, uh, the fraction like so a fraction term kind of also takes some kind of comes into the picture where like the fraction is over the number of satisfying assignment divided by total number of assignments. So if the formula has very few satisfying assignments, like let's say so there are total 2 to the n assignments, out of which let's say only 3 assignments are satisfiable, then actually in those cases like if you're taking a lot of things uniformly at random, then what's going to happen is it's it with a like if you're taking just polynomial number of samples, it's very high chance that you won't be taking sampling any of these 3 satisfying assignments out of the 2 to the n assignments. And so your algorithm will always output that. So you'll always taking unsatisfiable like assignments which do not which are not satisfying. And because of this, your algorithm will give like that the number of satisfying assignments is zero for this DNF form, which is like pretty bad. Like if the actual answer is three and you're giving zero, then it's a really bad approximation. Because what we need to do is like what we usually want is to have a approximation like a constant factor approximation or something. So like zero is not any multiplicative approximation for the value three. So that's why if there are like few satisfying assignments, this kind of approach will actually fail and give us like pretty bad results. And then it was discussed in the lectures like what's maybe an alternative way to go about this problem to have a like a better algorithm to have better estimates for this DNF counting problem. And for this, it was discussed that yeah. So let's see one till CMP the M and clauses which are like in the DNF form which are all like joined by union. So our DNF formula is given by these AND clauses C1 till CM. And so suppose the clause CJ contains TJ literals. Uh, then and let SJ be the set of all satisfying assignments of CJ. So what do we mean by this? So there are total n variables, and yeah, so if the formula CJ contains TJ literals, then these TJ literals are just and like so suppose like it contains three literals x1, x2, and x3 not, like not of x3. Then like we need to, since this is and we need to set all of these variables to true for this formula to evaluate to true. So x1 will be set to true, x2 will be set to true, x3 will be set to false. But all the other variables like x4 till xn can take any value, true or false. So these TJ variable literals will have to take like specific values, but all other input variables can take any of the values true or false for this formula CJ to evaluate to true. Then that's why the set of all satisfying assignments is Sj, and the size of this set Sj is just 2 to the n minus Tj. Yeah. And yeah, why are we defining the set? Then it was discussed like suppose you define a universe set U, which is just the set the set of j comma a, where j is like the index for like the clause. So there are like total m clauses. So the value of j goes from 1 to m, and uh, the value a is just one of the satisfying assignments of Sj. So Sj is like the set of all satisfying assignments for the clause Cj, and if you take any of one of those, then it's like A. So the set U is just the set of element j comma a, and then what's the size of this set U? It's just like yeah, so it's just like if you take j equal to 1, then this is just a satisfying assignment for the clause 1. J equal to 2 corresponds to the number of satisfying assignments for the clause 2, and so on. So the size of set U is just like size of S1 plus size of S2 till size of Sn. Right. But this is like not a very good estimate for the number of satisfying assignments. And why is that the case? Because yeah, it might be that S1, S2, S3, S4, and so on might all have like same set of satisfying assignments. Like S1 is also true at some specific assignment, and S2 is also true. The clause C2 is also true at some specific assignment. So that assignment will occur in both S1 and S2. So this value, like the size of U, is an overcounting of what we are actually what we actually want to count. What we actually want to count is uh, the number of satisfying assignments, and this is an overcounting. What we like, so yeah, so what we really want to count is the size of the union of these sets, the size of union of S1, S2, S3, and all, because this will give us uh, all the satisfying assignments for our DNF clause. Because for DNF to hold true, at least one of these C1 till Cm should be true. And for that, at least one of we have to take one of the values of the set Si. And that's why this gives us this is the value which we need to estimate, the size of unions of these sets. And we can't do this directly because these sets are exponentially large size, and that's why we'll employ some randomized approximation techniques. So yeah, and note that yeah, this set union of S1 S union of SJs can also be written in this form yeah. So whatever is this like maybe let's not get into that. You can uh, go through the lectures. You can watch the lectures later. But what one can actually show is the thing which we want to estimate, which is this thing, the size of union of S1 S2 till Sj. So actually, the size of this set, so that set is also called the set. Let's say this union set is, I call this set as capital S. Like, let's say I call this set capital S, then actually one can actually show that the size of capital S divided by size of capital U, capital U was this set, which we already know. Yeah, the size of the set S divided by size of set capital U is actually greater than equal to 1 over n, where m is number of clauses. And if this kind of a ratio occurs, then yeah, and we know how to estimate the size of U because size of U is just like summation of the sizes of these SIs. So we know what the size of U because these SIs values we also know. So if we know this value U, then this set S's value yeah. So then this ratio like essentially like so what I'm going to say is so like now maybe calculating the size of S if we know the size of U is somewhat easier because this ratio is greater than equal to 1 over m, so we won't run into the kind of issues which we had run into earlier. Like if there are like very few number of solutions, then we won't be able to sample them. Yeah. So essentially the high level idea now for the algorithm is like yeah, let's say we sample any satisfying assignment uniformly from the like set U, and how do we do this? First you uniformly randomly so first you sample any j with probability size of Sj divided by total size of like all Sj's, and after picking j, we pick a solution from Sj with uniformly randomly. And what this ensures is that every element from the set U is sampled uniformly randomly. And now what you actually do is like, yeah, initially the naive algorithm was to sample any arbitrary assignment uh, uniformly randomly and then check whether it is satisfiable or not. But right now what we are doing is we are taking the set of all satisfying assignments. Like we are taking not the set of all satisfying assignments, but yeah, a bigger set than that, which is the set U. And we are sampling uniformly randomly from this set U. Yeah. And what we say is that, yeah, if we sample L points uniformly randomly from this set U, then out of that, if K points belong to the set S, then then our output will be K over L times U. Yeah. So, and what was this set S? Yeah. So this set S actually did not correspond to these union of SJs, but its definition was something different. But the essential idea was the set S uh, can act as a proxy for the size, like since the size of the set S is size of the original union which we wanted, this set S can act as a proxy for this set. And the size and this yeah, the definition of this set, as you can see from the lecture, like I don't want to get into that, but yeah. So essentially, what we do is we sample uniformly randomly from this set U, and we check whether from these so suppose we sample L points from this uniformly randomly, and then if K points out of these belong to the set S as well, then uh, our output is essentially an approximation to the size of set S, and it will be just equal to since size of set S divided by size of set U is K over L, then size of set S is just K over L times size of U. So this is the high level idea of the algorithm for DNF counting. So you define the set U, you define the set S, and just uniformly randomly sample from the set U instead of like uniformly randomly sampling from any arbitrary assignment. And actually, now it can be shown that this algorithm is an FPRAS. Like, yeah, the algorithm for DNF counting, like this algorithm is an FPRAS. So we won't be going again into the proof of that. But yeah, but for this, for proving this, for proving this, uh, for proving this claim, there was another theorem there was another like really important theorem which was discussed in the lectures, which was called the estimator theorem. So essentially, what this estimator theorem says is that suppose we are given a sample space omega and some subset S from that omega, and we want to estimate the size of S using samples drawn uniformly randomly from omega. And suppose we have like the size of S divided by size of omega is greater than equal to some value uh, rho, which is greater than 0, then Monte Carlo method provides a epsilon delta approximation if it draws at least 3 over rho epsilon square ln 2 over delta samples. So again, this can be proved by Scherner bounds and everything, but one important property here is this thing, the size of S divided by size of uh, omega should be greater than equal to rho for this thing to hold. And like and this is where our initial naive approach failed, because in naive approach, like the size of set S the size of satisfying assignments can be really small. It can be 1, 2, 3, any small constant, and the size of omega, the set of all satisfying assignments, is like 2 to the n. So then this thing becomes like very, very small, this ratio. However, in our updated algorithm, which we claim that it's an FPRAS, this value is not too bad. It's like greater than equal to 1 over epsilon, 1 over m. So yeah, it's still not exponential in n. And that's why this algorithm provides like good bounds for this. Yeah. And for this, we need to draw like only this much samples. Yeah. So this again, its proof is not too difficult. It can be done using Chernow bounds and all, but yeah, let's not go over those. Yeah. And in all these algorithms, we should discuss estimating value of pi or estimating the count of DNF solutions. What we assume was an ability to sample uniformly randomly from some appropriate set. So, for example, in estimating the value of pi, we were sampling uniformly randomly from the square, and similarly in this DNF counting, we were sampling uniformly randomly from the set U. However, it might be that for some problems, we might not be able to sample uniformly at random. Like it might be difficult to uh, obtain a uniformly random sampler for the given problem at hand. So for that, there is another notion which was discussed in the lectures. It's called approximate sampling. The approximate sampling is like for example, right now we were trying to we had like some sampler or uniform random sampler, and we were trying to approximate the values. We were trying to approximate the target values. For example, we are trying to approximate this value v of x, and we are trying to provide an approximation for this v of x via our algorithm a of x. But our algorithm a of x, in the cases which we discussed, used some uniformly random samplers. But now maybe uniformly random samplers are also not available for us. Then we'll need to approximate the uniformly random sampling part also. So there are levels to this. Like first we are trying to approximate the target value, but now we are also trying to even approximate our sampler. And what's a and here there is a notion of fully polynomial, almost uniform sampler. So for example, a sampling distribution is called an epsilon uniform sample if yeah if the uh, total variation distance of our distribution P and the uniform distribution, so this mu is the uniform distribution over the space omega, like if the total variation distance is less than equal to epsilon, then yeah, our distribution is called like epsilon uniform. uh, our sampling distribution is called epsilon uniform distribution. And like essentially what this means is that like yeah, so the our distribution is like epsilon close to the uniform distribution. So like if the total variation distance is like at most epsilon between like our distribution and the uniform distribution, then essentially like we are epsilon close to uniform distribution. So yeah. And a sampling algorithm is called a fully polynomial almost uniform sampler, which is called FPAUS. If for every input instance x and epsilon greater than 0, it outputs an epsilon uniform sample in time polynomial in x and log of 1 over delta. So yeah, so it should output an for any given input instance x and epsilon greater than 0, it should output an epsilon uniform sample in time polynomial in size of x and log of 1 over. Oh, it should not be, I think, log of 1 over delta. It should be log of 1 over epsilon. Yeah, but you can check this in lectures as well. Because I don't think there's any delta parameter here. So yeah, it should be 1 over epsilon. But yeah. So, uh, for example, for example, for this approximate sampling, we had already actually seen an approximate sampling thing in previous week. Where there were discussions around like uh, sampling, uh, where there was a problem of like sampling an independent set at random. Suppose we want to uniformly randomly sample an independent set from the given graph. So for that for that in the last week's lectures it was shown that yeah, one can like uh, sample, one can obtain a distribution where each independent set is obtained with a like uh, probability almost uniform or like epsilon away from uniform, like it was discussed in last week's lecture. So yeah, that was an example of like approximate sampling. We wanted a uniform sampler, but what we were able to obtain was like not the exact uniform sampler, but yeah, something close to uniform. And using these approximate samplers also actually one can obtain these FPRAS kind of algorithms. So, for example, it was discussed in this week that suppose wants to count the number of independent sets in the given graph. Suppose we are given an undirected graph and we need to output the number of independent sets in the graph. For example, in the in this given graph ABC, yeah, what are the independent sets? So independent sets are like essentially the vertices which do not share an edge. So like the set of vertices which do not share any edge. So for example, the empty set is an independent set because now there is no vertex, so there is no shared edge. Similarly, like these singleton vertices are always independent sets. And then like this A and C, the set of vertices A and C is an independent set in the graph. So total number of independent sets for this instance is like 4. Yeah. Yeah. So now the problem is, yeah, suppose one wants to design a fully polynomial approximate uniformly random samplers for independent sets, because then this can help us in counting the like number of independent sets in a graph. Yeah. And yeah, so in last week's sessions actually, yeah, this problem we almost solved this problem because like our goal is to design almost uniform sampler from omega. We design a Markov chain with state space omega in such a way that uniform distribution is the only distribution, and the Markov chain is aperiodic and having small mixing time. And designing such a Markov chain, like we have already seen a Markov chain on independent sets in the previous week, whose stationary distribution is indeed the uniform distribution. So essentially, most of the tools for obtaining a fully polynomial approximate uniform sampler for independent sets was like discussed in last week's session, last week only. Uh, and in this week, we will just so you can see like how do we move from here in the lecture videos, but essentially uh, uh, just analyzing whatever was done last week. Like uh, in this week's lecture, it was just what we did in the what we did in the last week lecture was just analyze like everything in the polynomial time and what are the probability bounds and so on, which resulted in a like FPAUS for independent set. So yeah. Sorry. And yeah, like uh so yeah, I don't think there is. Yeah, so like again, this is just a repetition of what I just said. So we had a Markov chain with uniform distribution and stationary distribution, and if we had some uniformly random uniform sample, some like epsilon by 6 to the uniform sample from this set, then yeah, one can actually generate like, so this is just a continuation of like what I was saying here. Like uh, we had like a Markov chain uh, for independent sets in the last week session, and then we are just trying to analyze that Markov chain and see like how do we obtain a fully polynomial approximate uniformly random sampler from those. So yeah, yeah, like it's a really nice to have. So okay then, like since like I'll not, of course, not going to the analysis of this. You can just watch the lecture videos for uh, understanding the analysis of all of this. But yeah, so these were the only concepts which was discussed in this week's session. So yeah, since there is no one present in person in the session, so I guess yeah, we'll just usually I pause for like if someone has a doubt or something, but if no one is there, then we can just yeah move on to the questions for this week. So there are some questions related to independence and all. So maybe we can start discussing them now. So the first problem is the cover time of a random walk on a dense graph with n nodes and theta n square edges is. So what's the cover time of a random walk on a dense graph with n nodes and almost n square edges? So we already saw that yeah uh, the like consider a random walk on an undirected graph, then the cover time is at most four times. So we had this theorem. The cover time is at most like four times number of edges times number of vertices. So we know that cover time is at most this quantity, and we are given that the graph is dense. It has almost n square edges. So if we substitute number of edges by n square, then you get like four times n cube as the upper form, almost. Yeah, yeah. So maybe I should just add here as at most. So yeah, as discussed in the lectures, cover time is at most four times number of edges times number of vertices, and here number of edges is like theta n square. Uh, Hence the cover time is like order of n cube, like because n square times n will just be n cube, so it's at most n cube. Yeah. So maybe not underline, but yeah, I'll just bold the correct answer. So yeah. And why am I like not writing theta, but I'm writing order? Because like big, I'm writing not theta, but I'm writing big O notation here. This is because yeah, uh, we know that the cover time is at most four times m times n, but it might be that in some cases it is like not really this large, but it's like somewhat smaller. So there can be special graph topologies where cover time is smaller than these quantities, and that's why yeah, it is at most n cube, but yeah, it can be maybe smaller. It can be n square or n to the 2.5 for some specific graph topology. That's why I just wrote like order of n cube right now. In worst case, of course, it can go to n cube, but it might be smaller than that in some cases. Okay then. So after this, maybe let's move on to the second question. The second question says that what is the number of independent sets of an undirected graph with 10 vertices and one edge? Okay, so yeah, it's not too hard of a question, but yeah, like, it's still an interesting question. So the question asks what is the number of independent sets of an undirected graph with 10 vertices and one edge? So so let's just assume like we have a graph. Suppose uh, we have a graph. So it has 10 vertices. So let's say the vertices are like v1 till v1 v2 till v20 v10, and uh, and there is exactly one edge. So like we can assume without lots of centrality that the edge is v1 comma v2, right? And now our goal is to like, and this is without loss of neutrality because there will exist exactly one pair of vertices between which there is an edge. So then we can choose it to be any pair of vertices. Yeah. And now we have to find out the number of independent sets in this graph. So yeah, uh, the only way so consider any set S of vertices. Then uh, S is, so for this specific graph, then S is not an independent set if and only if. So this is my claim actually, like, and this is not too hard to prove. Like, if and only if both v1 comma v2 belong to S. So if both v1 and v2 belong to S, only then is it not an independent set. Because if both v1 and v2, let's say, belong to the set S, then there is an edge between v1 and v2, and that's why uh, the set S won't be an independent set. But if at least one of v1 or v2 is absent from the set S, then no two vertices will share an edge. So, uh, so maybe, yeah, I will say that, like, yeah, this for this claim, you should try to prove yourself because this is not too hard, and I just provided the high level intuition for this. Yeah. And from the above claim, uh, we get that what do we get? We get that number of independent sets of G is nothing but uh, 2 to the n, which is like the total number of vertex sets. So this is uh, the total number of vertex sets which are present in this graph. And from this, we have to exactly subtract the number of sets in which both S1 and S2 are present, minus number of sets uh, containing both V1 and V2. And what's this number equal to? So this is, yeah. So 2 to the n is nothing but, yeah, maybe I should not write 2 to the n, but rather just 2 to the 10 should be sufficient. So this quantity is just equal to 2 to the 10 minus number of sets containing both V1 and V2. So if both V1 and V2 are contained, then there are 8 remaining vertices, and we can choose, there are two choices for each of these vertices, either they can be included or they are excluded. So there are 2 to the 8 choices. Yeah. So this is the final answer for us. So this is 2 to the 10 is 1024, 2 to the 8 is 256. Yeah. So this is just 1024 minus 256, which will be 512728, I believe. Yeah. 928978. It will be 7. No, it won't be 728. It will be, I think, 768. Yeah, it will be 760. So yeah, so this is our final answer because any set of vertices is not an independent set. It can only if both the vertices belong to S, and like how many sets does both V1 V2 belong to S? It's just like both V1 V2 are in S. Then for the remaining vertices we have like two choices each for each vertex, whether it wants to be in S or whether it is in S or it is not in S. So yeah, so this is the answer. Then moving on to the third question, we have third question says that what is the maximum number of what is the number of maximum independent sets of an undirected graph with 10 vertices and one edge? So what is the maximum independent set? So it's an independent size set of maximum size. So yeah, I think the definition has not been like I think it has not been defined in the lectures properly, but it will come up in later session. So a maximum. So maybe I should just write it. A maximum independent set is an independent set of maximum cardinality. Yeah, yeah. So out of all the independent sets, you consider those sets which have maximum cardinality. And how many maximum cardinality independent sets are there is the question. So again, so we have a graph with 10 vertices and one edge. So suppose, yeah, without loss of generality, we can assume that the graph has like vertices V1 till V10, and the edge is just V1 comma V2. Uh, then like uh, consider the set of these vertices. Then the set V2, V3 till V10. So this is a set of vertices. Is an independent, and this is also an independent set because no two vertices share an edge. Is an independent set of size 9 because there are 9 vertices in this set, right? And also there can be no independent set of size 10 because if there's an independent set of size 10, then essentially we're including all 10 vertices, but including all 10 vertices includes both the vertices V1 and V2, but V1 and V2 share an edge. So this is not possible because V1 comma V2 is an edge. Is an edge. And what this means is, so what you're trying to find out is, first we are trying to find out the maximum cardinality independent set, and then we'll see how many sets are possible for such size. Hence, mm, the size of maximum independent set is, or maybe maximum independent set is of cardinality 9. Yeah. So this is the first statement. Yeah. Uh, but this is not the answer. Like we don't need to find out the size of the maximum independent set. We want to find out number of maximum independent sets. And then so we need to find out what are the independent sets which have size 9. How many independent sets have size 9? So you can see that if you want to have an independent set of size 9, then you actually have to leave out just one vertex out of these 10 vertices from the set. And note that you have to leave at least V1 or V2 out to be an independent set. So either you leave V1 out or you will leave V2 out. So there are just two possible sets. So there are only two. So yeah, so the answer is actually two. So there are only two maximum independent sets in the graph G. And what are these sets? Uh, Sorry for this, guys. What will be these sets? So these sets will be like the first set will be uh, the set which we already described. Maybe that is set this, and in the second set V2 will not be there, but V1 will be there. The set this and this. So these are the two sets which will be the maximum independent sets in the given graph. So, yeah. So 2 is the answer for this question. And I've just written like that. Yeah. Maybe yeah. So I hope it's clear to everyone. Then maybe we can move on to the next question now. So the next question says that what is the number of minimum independent sets of an undirected graph with 10 vertices and one edge? So this is kind of a trick question. Like one might say that like one might try to think a lot about like what's the minimum possible independent set, but it's like straightforward answer uh, uh, answer is one. And why is this? Uh, because the minimum independent set will be actually independent set of minimum cardinality, right? But we know that uh, like the empty set or set of no vertices is also an independent set, as we already saw in the uh, counting problem. Where was that? Yeah. For example, here in this graph, like we saw that like this empty set is also an independent set because set of no vertices is also an independent set. Since empty set is the only independent set of uh, cardinality 0. So yeah, so the answer is 1. And the set which has this minimum independent set, so this is for independent of the given graph. Like for any given graph, there will always be one minimum independent set, which will be the empty set. So this is not the case for just this graph, the specific graph, but this will hold true for any graph. Whereas for these two questions, we needed this specific graph, which had the 10 vertices and one edge. So yeah, just a fun question. Okay, then moving on, let's move on to the fifth question. Fifth question says that a polynomial time algorithm for the CNF counting problem would imply a polynomial time algorithm for the DNF satisfiability problem. So is this true or false? So one thing to note is that like what we have discussed already in the lecture. So one might think, okay, this has already been discussed in the lectures, but note that in the lectures we had discussed not DNF satisfiability, but rather DNF counting. So here the problem asks us not about like DNF counting and CNF satisfiability, but rather the opposite. Like it's talking about CNF counting and DNF satisfiability. Like so it's the opposite actually. Like the counting and satisfiability are exchanged in this question. So so we'll have to think a little bit about it. It's not like directly straightforward from the lectures, but like, although the high level idea is also mentioned in the lectures for this. So the problem is the polynomial time algorithm for CNF counting would imply a polynomial time algorithm for DNF satisfiability. Is this true or false? So actually, uh, uh, yeah. So actually, the answer is true. And why is this the case? Because yeah, because the claim, there was already a claim which we discussed, right? That uh, because if let's say we are given a formula f, like this guy, if f is a CNF formula, mm, so uh, like uh, then F bar or like not of F. I'll denote not of F by this, F bar as this instead of like, yeah, instead of like F and bar because like I don't want to draw the bars. Then F bar is a DNF formula and also not of F. Like similar lemma to what we had in the lectures, like one can claim similar lemma here also. So I'll just write down the lemma first. Not of F mm, is satisfiable if and only if uh, F has less than 2 to the n satisfying assignments. So yeah, so uh, like previously what we discussed in the lectures was like F is what was discussed in the lecture was F is satisfiable if and only if not of F has less than 2 to the n satisfying assignment. But actually the reverse is also true. Like not of F is satisfiable if and only if F has less than 2 to the n satisfying assignment. And this is because like you can just swap F with not of F and the claim will still remain true. And also like if F is a CNF formula, then not of F is a DNF formula. Yeah. So that's why uh, uh, and like so this is not a too hard to prove. So this is something you should try it yourself. Like this is straightforward from the lectures, but yeah, I've also given the intuition. But shit, you should try this here. Yeah, yeah. And because of this, because of these two things, like it's like ends the statement whole. So yeah. So this is how one can prove that like uh, polytime algorithm for CNF counting would imply a polytime algorithm for uh, DNF satisfiability. But it's not the other way around. Like if you have a DNF satisfiability solution for DNF satisfiability, it does not mean you have a polytime solution for CNF counting. And this is because if you have a polytime solution for DNF satisfiability, it just means that the CNF formula has less than 2 to the n assignments, but it does not tell us exactly how many assignments are true, which is what the CNF counting problem asks. So one can just compare whether CNF has like exactly 2 to the n or less than 2 to the n, but it cannot actually give us the count if one solves the DNS satisfiability problem. So this is an important thing to note. Like I wouldn't be writing it down, but yeah, you should keep this in mind. So okay then, I guess this was all I had for today. So we discussed like these 5 questions and summary of whatever was discussed in this week's lectures. So since there is quite a bit of time left, like I usually put out some time in the sessions so that if someone has any doubt they can ask. But since there is no one in the session, like of course there are no doubts. But nonetheless, I'll wait for like maybe 10, 15 minutes, like at least 10 minutes. Because if someone wants to join the session in person and ask some doubts, then like I'll be taking them off. So if no one joins, let's say the session like next 10 minutes, I will be closing the session. But till then, I'll just mute myself. So yeah. So I'll like if anyone wants to ask any doubts in session in person, I'll be waiting for 10 minutes. Okay, so I guess like no one has since no one has joined the session in person for any doubts, I guess I can just close the session now. So thanks a lot to everyone who's watching on YouTube. I hope to see some of you present in person in next session. But yeah, so yeah, till then, see you guys. So thanks a lot for joining. Bye bye, everyone.